let's cover up what we know so far and work together. So nitrogen and 3 hydrogen are in equilibrium with 2 ammonia. And this K is 3.7 times 10 to the 8th. Temperature hasn't changed. Equilibrium constants are generally given at 25 degrees, which is about room temperature. This expression, I take the concentration of ammonia squared set over the concentration of nitrogen to the first power times the concentration of hydrogen cubed. This is the equilibrium expression, no numbers, but this is where they're pulling it from, products over reactants, where the coefficients become the powers. It's telling us this is 3.7 times 10 to the 8th. When I have a 1 to 3 to 2 ratio, that's our product. So what would the value be if the reaction instead had these coefficients? Ammonia, 0.5 nitrogen, and 1.5 hydrogen. Alrighty. So a couple of things. If this was the original value, how do we make this equation? Alrighty. So if the forward direction gives us 3.7 times 10 to the 8th, with a 1 to 3 to 2 ratio, how do we create from this equation our target? Well, if the target is ammonia on the left side, the original equation has to be flipped. Also, if the original equation, our target here, has 1 in front of the ammonia, I'm going to have to distribute a 1/2. And if I take 1/2 of this target, I get 1/2 of nitrogen, 1.5 hydrogens, and 1 unit of ammonia. So I know I need to flip the direction, and we have to distribute a 1/2. To turn this equation, a 1 to 3 makes 2, into the target, we flip the direction and distribute a 1/2. All right. When we flip the direction, we take the reciprocal. So the first thing we did when we flipped the direction, we took the reciprocal of the original value. And when we distributed a 1/2, we took half the amount. We have to raise it to the power of 1/2. Flipping the direction says 1 over the original equilibrium constant. Distributing a 1/2 through the coefficient says raise it to the power of 1/2. And let's hit that on our calculator and see what we get. 1 divided by 3.7 e to the 8th power. Alrighty, take that and raise it to the 0.5 or 1/2, however you want to type that in. We get an answer 5.19, I'll say 5.2 times 10 to the negative 5th is the new equilibrium constant for the target equation. 5.2 times 10 to the negative 5th power, taking half of the original, taking the reciprocal, raising it to the 1/2 or square rooting, whatever you wanted to do to hit, gives us the new value for our target equation. Here's another practice. I think what I'll do is just keep a clean sheet because this looks pretty well overwritten. We'll keep a clean sheet and try to talk through this example. When a reaction A is in equilibrium with 2B, A goes to 2B, it reaches equilibrium when the concentration of A is at 1.0 times 10 to the negative 5th molar units. The concentration of B is 4.0 times 10 to the negative 1 molar units. When this reaction reaches equilibrium, they're telling us the concentration values. We could immediately think about calculating its equilibrium. The concentration of B squared set over the concentration of A to the first power, products over reactants, where coefficients become powers. We can substitute in those values, 4.0 times 10 to the negative 1 squared, set over 1 times 10 to the negative 5th raised to the first power. Let's hit that and see what the original value is for this equilibrium. So 4e negative 1, 0.4, and then we'll square that. Divide by 1e negative 5. And we get a value for equilibrium of 16,000. Again, no units, it's just a number. The larger the number, the more we're favoring the products. This is quite a large number. We're favoring the product side. When the reaction 2B is in equilibrium with Z, it reaches an equilibrium when the concentration of B is 4.0 times 10 to the negative 3 molar units. Concentration of Z is 2.0 times 10 to the negative 6 molar units. Let's calculate its equilibrium, where the concentration of Z raised to the first set over the concentration of B squared, plugging in those values, 2.0 times 10 to the negative 6th over 4.0 times 10 to the negative 3rd squared. Let's hit here and get a common answer and compare. Put that in a parenthesis. Oops. 4e negative 3 squared. I need that to be a parenthesis. I hate calculator issues. Sorry, apologize for the delay. Now I've got it, 0.125. Let me check my screen, make sure I hit it right after all that backing up. 2.0 times 10 to the negative 6 divided by 4e negative 3 that has been squared. We get a value of 0.125. That's a number smaller than 1, so it's favoring the reactant side. Alrighty. Calculate the equilibrium constants for each of these reactions. We indeed have 16,000 for equation 1, 0.125 for equation 2. Now, let's target in equation 3. 3z in equilibrium with 3a's. How can I use these elementary reactions to create Z turning into A with 3 of each? We'd like to know its equilibrium. Alrighty, so we have the basic building reactions. How do we place them together to get Z turning into A? Well, a couple of things I notice right off the bat. I have in equation 2, I have the product Z. I need it to be a reactant. So I know I'm going to have to flip the second, and I'm going to have to distribute a 3 to get the correct number. In equation 1, A is on the left side. We'd like it to be on the right side, so I've got to flip the direction again and distribute a 3. Taking this value, 1600, when we flip the direction, I take the reciprocal of 16,000. I'm going to cube that value because I distributed a 3. Flip the direction as reciprocal, distribute a 3, we're going to cube it. Same idea down here. The original value, 0.125, we flipped the direction, so I take the reciprocal. We distributed a 3, so we cube the original value. To find the target, it's K1 times K2, those new calculated values. When multiplied, adding equations together tells us to multiply